Yes, can everyone hear me?
Absolutely.
No reaction, maybe my sound, but
Yeah, all good.
okay, thanks. Okay, yeah, there is the chair. You can sit closer. So I was ill, but now I'm more or less healthy again. My lecture. So in the next three lectures, we will speak about parameterized algorithms. So there is a book in the references. It's a very interesting book. It's high level. So if you can solve exercises, you're very clever. So yeah, yeah.
I mean, it's a hard book or it's
It's for master students, definitely. Yeah. You need so there are
I
exercises.
thought that you mean like high level programming languages and all that.
Yeah. Okay, we're just chatting a bit because wow. I think someone will be sleeping soon. But it's nice, though. Yeah. Yeah, there is another chair there. The one out. Yes. Yeah, and here on here also somebody can sit. Yeah, my favorite place is here. Do I get all corners? So the topic of today is class activity. So I will get some examples, and then I will see what is kernel technique. The technique to make the input of your problem smaller. And so I did some project with company, and I like some of these ideas, and they were extremely happy and giving me a lot of money.
Isn't it the same as a kernel tree?
Principal component. No, it's a kernel of matrix. There are huge number of things that are called kernel.
Yeah,
Like
there is even a number of things that are called kernel tricks, like for instance, support vector machines.
Yeah, yeah, just everything that's important is called kernel. And then we will speak about branching for vertex problem. So that's only three. And then in the seminar, we will do exercises about kernel technique. So making it. So there is a small theorem. So that problem has kernel if and only if it's in class FTP. So they're just, this is the definition and the theorem. But you will see that the theorem is strange and useless, but interesting. Okay. So let's first go. I explained it already a few times. So in the previous lecture, we spoke about checking whether a problem is NP-complete or NP-hard. And so when it's NP-hard, then we know that, no polynomial time algorithm. So what should we do? So we should give a warning to our boss, like, okay, what you asked me is algorithm. So I will, so I cannot give you a provably correct algorithm that's always fast. So that's too much. Okay, but then there were some solutions. So let's say what it means. So there is no algorithm that works in polynomial time and give optimal answers for all instances. So three things. We said it before, polynomial time for all inputs and optimal answers. So usually we want a production problem, like produce a minimal vertex score, produce an independent set that's as large as possible, and so on. Okay, so but from out of these three criteria, two you can have two optimal things. Make two satisfied and drop one.
For instance, we can consider an algorithm that doesn't work on all inputs, but maybe on some subset of inputs.
Yeah.
Or we can consider a greedy algorithm that doesn't always produce the optimal result.
But for example, so approximate algorithm, like for vertex cover, we saw something in the lecture about approximation. So we can take an edge and put both endpoints in the vertex cover, remove it from the graph, and then repeat. It's kind of greedy algorithm, and it gives approximate answer and runs in polynomial time, and it works for all graphs. So just exact answer we drop in this case. Then other alternative is to look at special cases. So when we look at our input data for vertex cover, maybe we're lucky each time our graph is a tree, and then we can do something with dynamic programming or just greedy algorithm, like put. Okay, I forgot. I should call that. Last time I also forgot and screwed up. Okay. Yeah. So and then the third technique is to drop polynomial time and to do exhaustive search. And I think that's the most fun one because you can then optimize the search. And then there are many, many nice techniques. So this book I just showed you, it's really cool book if you have time and and it's kind of rewarding, but time consuming job. Okay. And
So
so
now we are going to avoid the polynomial time.
yeah, we will speak about exponential time algorithms, and our goal is to make the exponent as nice as possible. And so let us start with some simple example, and it is again vertex cover. So let me repeat after some months what is vertex cover. So we are given a graph. A vertex cover is a set of vertices that covers all the edges. For example, this graph, does it have a vertex cover of size 3?
Yes.
Yeah. So this one, and
Any of the bottom.
yeah. Yeah. So do we have vertex cover of size 2?
No.
Can we decrease? I already asked you some months ago.
No.
No. And yeah, but it's kind of tricky to see why it is. So there are 6 edges. So if we have vertex cover of size 2, we need to pick 2 times. So the total sum of degrees should be 6. And so the only way we can do it is pick this and this, because there's degree 3 and degree 3. But then this one is not covered. And if we pick any other node, it has degree 2. So it's kind of clever way. Of course, you can check for all combinations in Canada. Okay. Yes. So in general, how can we solve vertex cover? We can solve it in n-tree space types. So this is binomial coefficient. So n is a number of vertices in the graph. And let me write the inputs that you already know. So the vertex cover problem input is a graph. And the question, so do there exist k nodes, graph and a number k? Do there exist k nodes that cover all edges? Okay, and we can solve it in brute force in time and choose k. So from discrete math, it is number of subsets of size k from n different elements. It's about, so good estimate of this number is, so here's this number at 2.71 and so on to the power 3. Okay, there's a some advanced estimate, and let's forget about it.
No, it's not. Why is this so? We know the direct formula, like M tutorial divided
Yeah, yeah, yeah.
and the K and K.
But just I want to say that this is exponential. For example, if k is half of n, then there is even a better estimate. So then it will be around. So n is n over 2 is 2 to the power n divided by square root n. So in the worst case, k is equal to this value. It's very slow algorithm. And so our plan is to do better than this. Okay. So now let us think about special cases where k is not too big. So we might be lucky our k is a bit smaller. And so in parameterized complexity, in the worst case, we have this situation. We try in parameterized complexity, we try to find a parameter, and when we believe this parameter is now small, we have more or less okay algorithm. Probably still slow, but if a lot of but if our boss says, look, this problem is really important, I want to pay a few CPU years, then we want to give exact answer. And so you can implement clever program. Or maybe CPU days or whatever. CPU items. Yeah. So there is a programming exercises for this lecture and for the last I mean, the last lecture probably will be everything. I still need to invent the exercise. But so the grader I will switch on when I come home. I need to.
How do we submit them?
By email. And then the grader will download the email.
Oh.
And send you a reply back with your score. And you can.
So we only have one.
No, you can submit many times and it remembers your email address and it will tell me what's the best score. I know that I should put up a server, but I'm not a programmer, so I just.
And it's probably harder than a server to post the things.
Well, I tried with server, but it was a mess. I don't know anything. But you know that for 15 years I have I worked like as a tutor, and I got so many stupid emails that I figured out to automatically reply with certain questions. And so I use this system.
Wow. Well, it's a non-trivial way, the most non-trivial I can think of. It sounds like you have 100 times more easier to set up a Yandex contest. Thing. But okay, it's great.
Yeah. Okay. Yeah. Yeah, probably your next contest. I know that I had another exercise and it was more complicated with several questions and several deadlines. And I had to use smart LMS and it was so annoying.
No, smart LMS is absolutely dead story. Doesn't work. Most of the time it just lays down calmly. And yeah, the Yandex contest, I don't know in detail, but very so
Yeah, you're right. Okay, maybe for the last lecture when I set up, I will use Yandex contest.
maybe consider it, maybe it will be simple.
But like I'm not so good in giving away control to some computer. I want to program the grader myself. But it can do randomized, like when you submit, I generate a few random graphs. So to see that you're not trying to read the inputs. Like, okay, I'm not gonna tell all the ways you can mess with the system.
Yes.
Okay, so yeah, it's distracted. Okay, what we want now is we have exponential searches, and there is nothing much we can do about the special case when we're at half of the nodes. We can do a little bit, we will see, but what we will assume is that there is some parameter, and if it's not too big, then our search is hopefully good. So we will tailor our search according to some parameter, hence parameterized complexity. Okay, and so first algorithm is for the vertex cover. So k is small, So we can do something better. There is an algorithm that runs in power 2 to the k for the of n. So for vertex cover. And so this algorithm is branching algorithm. And how does it work? Well, what we do is we will pick an edge. It's a very famous algorithm. And what do we know when we look at an edge? What do we know about the two endpoints and the vertex cover? Well, just by definition, every edge needs to have an endpoint.
Yeah.
In the
So one of the nodes
is
is going to be in the.
yeah.
Yeah.
And we can just pick one and then recurse.
Yeah. So we will recurse whether we believe that this is in the vertex cover or this is in the vertex. And then we can make our graph smaller and look for a smaller vertex cover. We already see why this is. If everyone sees it, that's really cool.
And it
Yeah,
does
it's a-
branch out in K.
Yeah.
K.
It's 2 to
But
the power of
that's-
a recursive branches, and with the
Yeah.
branch runs into the.
Okay, I will do something boring
It's
because we will need so many recursion trees that I will draw one. So because then we have to do special things. So let's take a graph.
Am I right that it can be non-binary recurse?
In general, yeah, but in this case, it's binary, right?
Yeah.
Yeah. So let us have a graph here. And then, so let us think that this is our graph.
No,
It can be non-binary.
Yeah. So, and then we can say, let us put this node in the cover and then remove all the edges that are already covered.
Mhm.
And then we will have, okay, so this is, let us say that this is the graph which we start. There are some slides, it's the same example. No, I need to. So let us look at this edge, and then there are two cases. So in the first branch, we remove this node, and what is left is this thing. Yes, that's left. And in the other case, we add this node, and then what is left is this triangle. Am I right? No. No, not much is left. Okay, and then we can take a new edge. It doesn't matter which one. Okay, so sorry, I didn't ask a question. So imagine that the input here is a graph, and we want to know if there is a vertex cover of size maybe 4 meters. 4. And then here, our instance is this graph and a vertex cover of size 2. So the answer to this question is yes. Then to this question it will be yes. If here it's yes, then this will be yes. If they're both no, then answer is no. And so now we can. So,
It's obvious that it's this and the left, then.
Yeah. So where shall we branch? Maybe on this one, because with nodes of degree 2, it's kind of boring. Or maybe even better on this one. Okay, we got it. So there is a case when this number, each level we go down, this number goes down by 1. And in the end, we have a tree, and the number of nodes is 2 to the power k. Well, the bottom, the number of leaves is 2 to the power k. The number of nodes is at most 2 to the power k plus 1, because it's binary tree. Okay. Yeah, and in every node we do a polynomial amount of computation. So what are the base cases? So when we go to k equal to 0, we check that we have dropped all edges. That's a base case. K gets 0, or there are no nodes left in the graph. That's also kind of base case. For example, no nodes and k is equal to 5, and then we say yes. And then it propagates up because every splitting is an OR. And to write this code is really short. So to get half of the score, you just have to write this. But you need no, sorry, it's no, sorry, it's a different algorithm. We will see it, but it's equally difficult to program. So
it's a brute force, but just adequate.
yeah, you need to. Okay, so you can also branch on the nodes. So you say either the node is on the vertex cover or all the neighbors are in the vertex cover. Yeah? If this node is not in the vertex cover, then these edges need to be covered. So all the neighbors need to be covered. And this gives a better branching algorithm. Better, yeah, always better. And not always better, but we will speak how we can ensure that's always better. So we will add something, and then we will get a better power than 2 to the power. But I'm going too fast and now. So our first goal is to say what is class FTP. So first I need to say what is a parameterized problem. And this is a problem where the input consists of two parts. One part is we call parameter, the other is just the rest of the input. And that's it. So before we spoke about languages, so a language is a subset of strings of some alphabet. That was all. Now a parameterized problem is a subset of pair where we have a natural number as parameter times sigma star. So this is parameterized problem.
One actually.
Well, we don't, yeah, usually it's not necessary to have real parameters. But we will see that the parameter is only used for some time bound, and then it's rounding doesn't matter. Okay, now what is the class FTP? So FTP is class of problems that can be solved. So there is some input X, there is a parameter K, and then there is some question. Here is the question, and the question can be answered. So a problem L is an FTP. If there is an algorithm that runs in time, a function of K times a polynomial of the length of X. So let me write it. F is language L. It's in the class FTP. If there exists a constant C and algorithm that resides L, then F of K times length of X to the power C. Oh, sorry, and we also need the function F. So, right? F needs to be a computable function. Okay. Yeah. So it's clear, right? What is it? So X is the input. Yeah. Yeah, so the constant. That is a computable function. Yeah, so it can be exponential. And so in our problem before, for vertex cover, we had 2 to the power K times 47.
So the language consists of some pairs, a natural number and a one.
Yeah.
And what is the natural number for?
For each problem, it's different. So in our case, K, okay. So the natural parameter is when we have some production problem, is the size of the thing we produce. So for vertex cover, the parameter is this K.
And X you
So,
can get.
so I mean, if we have a language, all the elements in this language have the same first element.
No, no. So K is a part of the input. K can be anything, but it's a special part of the input that we call the parameter.
Mhm.
And the requirement on the runtime is that the parameter does not appear inside the power. Or that at least there is a constant power.
The function f that decides L in f of t.
Yeah, so f is a function from natural numbers to natural numbers. We give it a parameter, and for example, 2 to the power k. So in this example, we have f of k, 2 to the power k. But it might be 2 to the power k, and so on. So if we believe k is not too big, then we have a polynomial times. For constant k, we have a polynomial, but it's a little bit stronger because the polynomial only depends on k in a linear. K doesn't appear in the power.
Why do you need f to be computable? Like f
Oh,
is
it's
just
for
a
some
boundary.
pathological reason. We won't need it, but there are some very unpleasant things.
So
The halting problem suddenly becomes weird things start to happen.
yeah.
Yeah, so we don't want undecidable the halting problem to be fixed. Yeah, so actually most books skip this, and most books they write actually this to the power c, but we won't need this.
Why can't we just say f of k times poly of x?
So
So
f of
any
k,
polynomial, yeah,
yeah,
times
and
any
that's
polynomial.
any
of x.
polynomial, yeah.
Yes, that's the same.
Yeah, it's the same. Oh yeah, maybe if x is like 1 or something, okay. But then we can hard code the answer. Okay, yeah, I'm a bit lazy.
And f can be any function, but it can be exponential.
Yeah, it's allowed.
What means FTP?
Fixed parameter tractable. Fixed. Oh, sorry. FPT. Yeah, sorry. FPT, fixed parameter tractable. So there are some slides for this lecture.
So we're checking if whether the pair k and x.
Yeah, it can be solved fast enough.
Okay.
So there is another class. You don't need to remember it, but it may be as nice for comparison. There is a class XP. It's called slice-wise polynomial. They add X because there was no other letters left. And that means that it's solvable in time X to the power f of k. I don't know how much. Maybe I should add big O or something. So the same definition, just a larger. This is called slice-wise polynomial. And so our algorithm that tries all subsets here, that was an algorithm that proves slice-wise polynomial. Because the runtime was bounded by x to the power k. This k is bounded by this thing. So independent set problem, so graph and a number k, do you find an independent set of size k that has no connections in the graph? It's slice-wise polynomial, and it's believed you can do no better. In the last lecture, I will explain how this is proven. Okay, let me write that. I have some example. I will just state some problems. So click with max degree. Sorry, yeah. Click with the natural problem. With the natural. Sorry. There is also a definition for two parameters in FTP. So if you have two parameters, k and alpha, for example, Then there are two ways to define it. So you allow f to depend on two parameters, or you have f with one parameter and you apply it to the sum of the parameter. And so an example is clique with maximum degree and the size of the clique. No, just with the maximum degree. That's a good example. So this is also FTP. Vertex cover we already said.
Max degree is the parameter.
Maximum degree of a node. So here it's 3 because
Yeah,
all nodes have,
it's the parameter of
the parameter is maximum degree. Then subset sum problem, like given a bunch of numbers, can we select a subset of these numbers that reaches exactly target value? And then if the parameter is a target value, then it's also FPT. And then the independent set problem, and there we have both the max degree and the size of the independent set. So there are 4 examples of problems that are FPT.
There is a typo.
Yes, I also.
Yeah. Oh, transport protocol.
Yeah. Yeah. We were talking too long about servers. Okay. So problems that are in so there are some problems. So it's problems in NP that are also in FPT. They're kind of easy. So you don't need to be desperate. But if they're outside FPT, then it's your life becomes much harder. For example, clique and independent set problem. So then you need to try to find more parameters that are likely to be small in the problem. Okay, so yeah, clique as clique size, a natural parameter, and it's not an FPT under some hypothesis called exponential time hypothesis. It says that SAT cannot be solved in sub-exponential time. I mean, roughly saying, it's slightly more subtle, but it's a very important hypothesis. So you often see it in papers. It's just 10 years or 14 years old or something. It's really something. And then the K colorability problem. So given a graph and number K, can we assign one of K colors to all the nodes so that every edge connects nodes of 2 different colors? So this problem is not FPT when K is a parameter.
It is NP complete, right?
Yeah, so tree colorability is NP complete. So assuming P doesn't equal to NP, we know that we cannot have this runtime, because if we set K equal to 3, it would be a polynomial. So assuming P is not equal to NP, not equal to NP, let me write it. P not equal to NP implies a colorability is not in FPT. Not in FPT. And it's also not slice-wise polynomial for the same reason. So here is the bound for slice-wise polynomial. If we set K equal to 3, we again have a polynomial. So in practice, we assume P not equal to NP, unless you really like SAT solvers or no solver or whatever. Yes. Okay, let's do one more example. Okay, some simple observations. So P is a subset of FPT. So can we understand this? So P is a subset of FPT. So there is a little formal detail. We don't have a parameter, but let's just put whatever in this parameter, like 1, constant 1, or the X itself, or whatever we choose. We always have that this is true. So why is it?
Because P is polynomial, we can just take F as identity, K is 1.
Yeah.
X of C.
Yeah. Easily. if P is equal to NP, then NP all the problems and so this is direct consequence. So whenever we want to prove a problem doesn't have a solution with this runtime, we will need to assume P not equal to NP. So this assumption, exponential time hypothesis, that SAT cannot be solved in sub-exponential time, it's a stronger assumption. If P equals NP, we can solve SAT in polynomial time. So this is we needed to say that clique is not a FPT. So we need stronger theoretical assumption. Okay.
Exponential time hypothesis is weaker than saying that P equals NP, right?
So P not equal. So
And B is a stronger assumption than exponential.
So yeah, exponential time hypothesis stronger assumption. So for example, maybe SAT can be solved in time square root of n, where n is the number of variables of the SAT instance. Then exponential time hypothesis is wrong, but it's still possible that P not equal to NP. So it requires every function
exponential times says what again, that it exponential on times of
so that there exists a scene such that
yeah.
solving SAT requires to okay, I should carefully study this because it's kind of subtle exponential time hypothesis. I mean, there are good reasons, so and I didn't look it up, so so let's do another example of a problem. So now one with two parameters. Or three. So let us look at a clique with a maximum degree as parameter and the size of the clique. So input. Okay, another thing I say that there are actually two variants where the parameters are part of the input and not part of the input. But we will always use part of the input just for simplicity. So max degree. And then the number k. And the question as clique of size at most. Okay, that's our problem. And now the task is to prove that using both so we know that without this parameter, it's not an FPT. But with this parameter, we can prove it's an FPT.
What is the degree of a node?
Yeah, so every node has degree at most some parameter.
Max
K is another, so yeah, so K, this is the size of the clique, and then the max degree. And so the question is, how can we prove it?
You got to do this into by providing some
Exactly. The question is which algorithm? So what is a clique?
is a connected component.
No. Connected component. Well, okay. Connected component in the graph is you pick a node, and all the nodes that are reachable from this node, they're called connected component. But a clique, but almost right. So just a set of nodes, and every pair of node is connected.
It's strongly no.
That's for directed graphs, that you can go from every node and the
yeah.
clique to the other and vice versa. Yeah. You can do some.
And a pair of nodes.
Yeah, it is connected by an edge.
So it's like a full
Yeah.
stop graph.
So here,
That's what I was trying
so
to
this graph has a clique of size 3
three.
contains
The
the
triangle.
because there is triangle, but it doesn't have a clique of size 4 because we need both diagonals. Or
No, we don't need both diagonals, we just need one of them. There will be.
no, this is not a clique. This is not a clique.
No, on the top.
Yeah.
Triangle and this.
No, on the top,
That's yeah,
yeah.
Okay,
Yeah, we need
yes,
6 edges, yeah.
But I have a
Okay.
question.
Now
Yeah,
there
yeah,
is-
now
yeah.
that's.
Yeah. Okay, so now we understand what's a clique. It's very important for this exercise. Yeah.
The question is, so the question graph has clique of size at most k, but if we have a clique a larger size, we can just take any subgraph of this clique and it will be
Yeah,
a clique also. So the question is just the graph has a clique of any size, right?
Sorry, at least, yeah, good point. Yeah, yeah, this is very important. Okay, and then there are values for k for which it's easy to answer. For example, what if k is larger than d? Then, yeah. Well,
Is really at least like
so if
k minus one.
Yeah.
We need some nodes with k minus one edges.
If we have d plus 2, we can directly say no. Yeah, because in triangle we have degrees 2, so then there is a clique of size. But when it's larger, then so it's already first hint, so we can assume k is at most d plus 1. And so I will tell you something. The algorithm runs in time 2 to the power d body and number of nodes in the graph.
Maybe something similar to branching, like take a node with max degree.
Find all the neighbor nodes with max degree,
Yeah.
and you check if they form a quick, because of it, like that.
Almost. Maybe
Okay,
somebody from home or from Zoom.
Okay, do we always need to pick a node with maximum capability?
Yeah. So
So like we need to pick nodes with k minus one at least, or more. K minus one or more. So yeah, and what's next? Okay, let's say we choose a degree, we pick a node, then we look at all the nodes, and if they're all the same degree.
yeah, what you say is recursion is good, but it's easier to answer. You can answer more easily. If you want to have this time, if you implement, maybe it's a good idea to speed up, but just say the easy stuff. Okay, I will tell you because you basically get it. So we just go over each node, and for each node, we check whether this node and some of its neighbors forms a clique. And so what we have to do is just check all k element subsets of the at most d neighbors.
Of k elements.
Yeah, so subsets on d elements is at most 2 to the power d. So we check all subsets of neighbors.
So, I mean, we just take a node and check if its neighbors form a clique.
Yeah.
If they do, then the answer is yes. If they don't, for all of the nodes, which is n.
Yeah.
Later.
Yeah, then the answer is no. Exactly.
Isn't it exactly n by 2 to the power d?
So it is,
Now we need to.
if you want better bounds, it is, we have the neighbors. And we have, so we have to choose scale of them. Yeah. K minus one, I think. So that's a better bound. Or we could do like you say with recursion and maybe we get, but no, because it's FPT, but now with length of X being D, so it will not so much gain, but when you implement it, maybe it's like in the end of your implementation, you can try to speed up like this.
So it means that then the less B then it better for us, yeah?
Yeah. Okay, but since this exercise go well, let's do the same for independent set.
Let's just take the inverse of the graph. We'll do the same. Graph has an independent set of cells B, it means that the inverse of the graph has a group of cells B.
Oh, yeah, that was fast. Okay, but I will continue to speak about, okay, so we finished with our first stories. Let's now go to kernel. And so I will make a different algorithm to prove that's an FPT.
Could you please remind us what is
Independent set. Yeah. So here's the graph again. It's a so it's a set of nodes for which any pair on the set is disconnected.
Okay, so you can
Yes. So for example, this graph has independent set of size 2. So this and this one is in because these two nodes are disconnected. But it doesn't have an independent set of size 3 because whatever pair we choose and whatever third node, well, we have only 5 nodes and there is a cycle. So if we choose 3 nodes, there must be, so there is a cycle. Even if we ignore this one, there is no independent set of size 3. Okay. Yes. So what I'm so now I will explain what is kernel, and I will do it with an example. But maybe I should use the vertex cover as example. Yeah, vertex cover. Oh, cluster graph. Yeah, let's do another example about FPP. I think it's a good idea to have for this definition. And so the problem we will consider now, input is again a graph. Parameter will be some number k. And okay, first the definition. What is a cluster graph? It's disjoint union of peaks. So example of a cluster graph is something like this. So that's kind of weird graph. Weird definition, you might think, but actually it's very useful, a cluster graph. So for example, in genetics or proteins, so people want to know whether genes or a bunch of genes belong to partition in animals. And then they check, they connect to genes if they're quite similar. And then each cluster are different animals from the same species, for example. But normally when they try to do this, there are some faults and there are some defects. So maybe it's something like this, and this connection might be a defect. And so here is the problem. Given a graph, can you delete at most k nodes to get a cluster graph?
You can use spectral clustering algorithm that visualizes the question.
Yeah, and so this problem is NP hard. So that means these answers are not always always correct for this discrete version of the problem. So the question can use these nodes to get a cluster graph. So cluster graph is joint union of peaks. And so here in this example, we could delete this node or this node. So that there, for these animals, maybe something went wrong in reading the genes. Like in the device, DNA for two species get mixed up or something. Okay. Yes. And so this problem is NP hard, but fortunately it's an FPT. So if we want exact answers, we can write an efficient algorithm. And there is an algorithm that runs in span 3 to the power k for the edge. So how does it work? Well, let us check what are the cluster graphs on 3 nodes. Let us look to all the graphs on 3 nodes. So I will make. So there are 4 non-equivalent graphs. And so 0 edges, 1, 2, or 3 edges. So which ones are cluster graphs?
The only one.
Yeah.
No,
First, second, and the last.
Yeah, indeed. But this is not cluster graph.
Because it is not fully connected, so it's not a click. Next one, not also between.
Yes. Okay. So now there is a little lemma. A graph is a cluster graph if and only if for every 3 nodes, every triple of nodes, we have one of these cases. So the induced subgraph is one of these 2 cases.
So we can just select triples and check the data.
That's indeed the algorithm. Yeah, can you think? So graph is cluster graph if and only if every triple of nodes either belongs to these groups. Or in other words, for every triple of nodes, this does not appear. So let's prove it by this true. Should I write it here? Or you can maybe, okay, let's write it. So the cluster graph, if and only if, for all W, the induced subgraph not W. So we just look at these 3 nodes, and then we know that if U is connected to V, V is connected to W, then it's not a subgraph. But if for every triple of nodes, we do not see this, then it's a cluster graph. So for example, this is not a cluster graph. What can we use for U, V, and W?
The circled ones.
U, V, and W. So because we have these 2 and these 2. And so how do we prove this? Okay, so let us say clear again, what is cluster graph? Every connected component is a clique. So that means that if we pick any 2 nodes that are connected by an edge, then these by a path, then they're connected by an edge. So again, if every 2 nodes that are connected by a path, they're connected by an edge. Yeah. So that's a property we need. And what we have here, we pick 3 nodes, and they're not connected by an edge. But then we have an edge. So here we take 2 nodes, W. But then it can happen that so this is not a cluster graph because we find 2 nodes, they're not connected by an edge, but they are connected by a path. So now we need to come up with 3 nodes. Okay, so to prove this equivalent. So there is one easy direction, one difficult direction. So easy direction is that if it's a cluster graph, we will not see this thing.
Yes.
This is obvious. Now, if we do not see this thing, then it's not a cluster graph. So let's go to the reverse. If we do not see this thing, then it's not a cluster graph. So no, if we do not see this, it is a cluster graph. Yeah. So the contrapositive, if it's not a cluster graph, we do see this thing. That's what we have to prove. Okay. So it's what he said.
Now, if it's not a cluster graph, we do see this thing.
Yes, it's not cluster graphs. Therefore, we see as 2 nodes with 2 disconnected nodes with common neighbor. So, and now, not cluster graph, we see this. That's what you have to do. Okay, so not cluster graph, we have 2 nodes that are connected by a path but disconnected. So how do we choose U, V, and W?
So we choose the U here on the sides and any there in between.
Yeah. So
Yes. Let's say this.
but we might be unlucky. We might have this. So we pick any node on the path, and if we're unlucky, no, then we are lucky. Yeah. But we might be unlucky, and there is no edge here.
Yeah.
But then we move W to here, and U and W become closer, so we can repeat. So let me say it again. So we have a path from U to W. And so we pick any node V on this path. In the middle, or if you want, next to W. And so there are 2 cases. Either V is connected to U, and then we are finished. But V might be not connected to U. And then we move W closer. Here. And then we again search for V, and we keep repeating until W will never be next to U, but it will be a distance.
Because if
Yeah.
we have V,
Yeah, when so we don't move when they're connected, so it will in the worst case it will go to distance 2. Okay, it's clear. Yes. And now you already said what is the algorithm. Yes. Yeah. So we will search for the forbidden triple.
Yeah.
If we find none, if we tried all triples and all of them are okay, all of them are of this type, then we conclude we have cluster graph. And otherwise we find such a triple, and then we try to remove each of these nodes. So we drop U, and then we repeat the process. So then we do recursion. So and we decrease k by 1 because we can now at most k minus 1 nodes. And so we will have a recursion tree, but now with 3 legs.
And what's the asymptotic complexity?
Oh, this is very easy. So
Definitely 3 to the power of
we can almost delete
to the power of k, 3 to the power of k.
Yeah.
And we find we check all the triplets by
time poly n.
Wait,
So we have 3 to the power k poly n. Where n will be a number of
we need to
nodes or
split
whatever.
3 out of at most n.
Yeah,
And it's
3 choose n, which is n to the power 3. So you make 3 loops over all the nodes.
And then
something else.
Okay, so there is a little break.
Типа там n факториал разделить на n минус 3.
Да, ну, okay. So half an hour. Yeah,
So, is it the break now?
Well, it's 7:14, so but I have, we only finished this one. But this one is quite short, so yeah.
You've just said that it's a little break and I just told you.
Yeah, I
I
thought,
can go
yeah.
and buy a coffee.
No, sorry, half an hour and then.
Okay.
Yeah. Okay, maybe I can open the.
А, ну да, ну это точно N3. Ну так что мы? Все, там типа, ну я же говорю, N на N-1 на N-2 перепишешь. Действительно полиномиал. It's a break now.
No.
Oh.
We will do a kernel and the funny definition and funny theorem. But first example for kernel with vertex cover problem. And again, the parameter is size of the vertex cover. Yeah, so it's 7:10 now. So the lecture is an hour and 20 minutes. So yeah, but we started a bit later and I will finish kernel for sure. And so graph parameter K has the vertex cover of size at most K. And now we have a very a topic that leads to a lot of money. I mean, just on my work account, so for hiring people. So it's, but if I want, I can transfer to my account, but just I bought some bitcoins. I don't see the point. 1 year ago, so the all I put all my savings in bitcoins, and then it was So I don't know why I'm working anymore because it might find times 3 or something since 1 year ago. Yeah, and okay, so I'm distracted again.
It's distracted by money. Is always money is still
Okay. Oh no, but I shouldn't say this on YouTube. Let's try to find accounts. Okay, I just got it out. Yeah.
What's the
Vertex
parameter?
cover? Yeah. So what is our plan now? We want to solve vertex cover problem, and so we had some runtime 2 to the power k times n squared, for example, or maybe a RAM model with careful implication is something like this. And so now we want to reduce this factor n. Okay, it's not so impressive maybe, but there is some general technique and soon it will become impressive. So the techniques will start to combine and suddenly it will be impressive, hopefully near the end of the lecture. Okay, and so for vertex cover, there are certain things we can do to make our problem easier. First example, so it's supposed to be a scissor. Let's drop all nodes of degree 0. Just they have no edges. We have not to do anything about them.
Can you repeat what's the parameter? Same as before?
Yeah, parameter
This size of the
vertex cover of size at most k.
Okay.
At most.
Yes.
At least like this.
No, now it's at most. So the the click and independent set should be large. The vertex cover should be small.
No, but we
complement.
have a vertex cover of size 1 and we always.
No. Of size and
No,
we always have.
No, not independent.
Yeah. But complement of vertex cover is independent set. So independent set you want to be large and the click should be large. Vertex cover should be small. Okay. So first rule, drop nodes of degree 0. Second rule, okay, sorry. Now it will be totally not impressive, but okay. So second rule, oh no, what was the second rule? If we have a node of degree k plus 1, what do we know about it?
k+1, k is the sum of the vertex cover. It must be in vertex
It
cover.
must be in the vertex. If we don't pick it,
Yes.
then we need to cover all the neighbors because the edges to those neighbors need to be
And it
covered,
is more than k.
and it's more than k. So next reduction rule, remove nodes of degree k plus 1 or more, plus 1, and k goes to k minus 1, and then recurse. So decrease k by 1. So we have a new problem. So we remove the node, we get a new graph, and we have a new value for k equal to k minus 1 of the old variable. And then these are equivalent, these problems. So in the new, so what we do each time, we get the graph and k, and then we map it to a new graph g prime and k prime. And the answer on these two graphs is the same. So if we drop a node of degree 0 and we keep the same k, answers remain the same. So we're just rewriting our input and each time easier. Okay, and now next rule. If graph has more nodes than, if a number of nodes more than k times k plus 1, say no. We can write away. So we apply these rules until it's impossible. And then we apply the third rule. So each time we see a rules like this, we do the first rule until we can. Then we apply the second rule. Then we again start from the top until we can, and so on. And so when we have applied this until we can't, and then we see there are k times more than strictly more than k times k plus 1 nodes left, then we just say there is no vertex cover.
Because k times k plus 1 is the number of edges on fully connected, twice the number of edges of one fully connected graph of size k.
It's twice the number of edges
On
on
the fully connected graph of size k, right?
okay.
Ah, no, it's
So the question is, why don't we make a mistake here? Why it's still equivalent? So when I say no, I just output empty graph with, or just graph with two nodes by an edge and k equal to 0, and then it's no. Yeah. So why is this right? Okay. So let us think that the answer is yes. What do we know about the size of the graph after we apply these rules? So let us think that vertex cover exists. So there are k nodes and they're vertex covered. K nodes, and they cover all the edges. We know that they have degree at most k. Same for this. So all of them go to k nodes. Okay, how can we have more nodes in the graph? So here we go to at most k nodes. So what's the maximum number of nodes we can have so that none of these rules can be applied? So here we know that the nodes in the vertex cover. So we assume vertex cover exists. And then we check what's the maximal number of nodes in the graph.
And
It's k times k.
yeah,
So we know that the degree of each node is at most k.
Plus 1. Okay.
There are no isolated nodes. And so this node can be connected to at most k nodes, and the same for here. So if the answer is yes, so if yes, then number of nodes at most k plus k squared. K plus k squared. And so this rule is correct. And this is great. So why is it great? We may start at arbitrarily large graph, And if k is small, we end up with the graph of order k squared.
If it's if the order if the order
Yeah.
is higher, then we
Yeah.
just have to know.
And so we can improve. It doesn't matter which c we use here. So we go from 2 to the power k to 2 to the power k to the power k squared to the power c. So we can have 2 to the power c. It doesn't look impressive to you at the moment. So if n is 5 million and k is 100, then
It
it's
makes sense.
yeah.
But yeah, but still, if k is 100, then it's 2 to the power of k, and it's still computationally difficult.
Yeah, but we're not finished yet. So we will get to k. Maybe not in this lecture, but okay. So 2k, 2 times k instead of k squared we can get.
No, I mean 2 to the power of k.
Yeah,
So it's
but we will have 2k. So we replace n by 2k. Yeah, so from 10 million to 100, for example. Yes. Okay, now let's explain what is kernel. So people are still looking to the board.
Yeah, I have a question. So on the second step, we just select some node that has a degree larger than k plus 1. What if we don't have such node?
Then we're finished with this rule, and we can go to this rule. So each time we start on the top, and when we can do something, we start again from the top. And if this rule can no longer be applied, it means that we can go to the next rule.
And if
no, we need to check the first one. No?
Yeah, after we apply this,
Yeah, we need to
we
check the
check
first.
on this, and
And
then after we check this rule, it cannot be applied, we go here. So that we will always make like lists of reduction rules, and we go each time through them. I mean, it's not always necessary. Like when you're programming, you can be more lazy, but you need to know the proof. You can choose the order.
Why don't we go to the top to the first rule again after?
Well, in here, the order of these two is not so important. We
Yeah,
can always change them, but this we can only do if this can no longer be applied.
None of this can be applied.
Yeah. But,
So basically, we apply the first rule, then we, as much as we can, then we apply the second rule as much as we can, then we go back to the first rule, and if we cannot apply the first rule only, then we go to the third.
that works also, yeah.
Otherwise, we just repeat the process.
Okay, and so now we can say formally what is
a kernel.
What is kernel? Some space. Let's write it here. Okay, email vertex cover. Okay, we'll map inputs over problem to the other inputs. So n times sigma star to n times sigma star, and k needs to be polynomial. If k is 40 times computable, and so what we want is that the parameter doesn't explode completely. Okay, there's some formal definition. We require the parameter to be bounded by computable function. Again, this weird technical thing. So and like this computable function, it's almost automatically satisfied, especially in our case where we have part of the input. Okay, computable function S from n to n. Such that so size p of x smaller than s of k. F. No. Sorry, F is kernel if. Okay, I didn't start my definition right. Let's move. Okay. Sorry for is kernel if sorry for there exists polytime computable if sorry if this so first condition is to be polynomial time computable. Second condition, there exists computable function f such that this is true. And three, it should be equivalent. So Ax and L, if and only if A of Ax and L. So these are three requirements. So that's definition. So sorry, it was boring when I was writing.
What's S of K?
So it's just some function, computable function from natural numbers to natural numbers.
Okay.
And so we want the size after the reduction to be only a function from K. So remember, in our vertex cover example, we had K squared for the size of the function because of this third rule. If it's larger than K times K plus 1, we directly give the answer. So directly give the answer just means that we pick an as the most simple instance where the answer is yes or no. And so if the answer is yes, we put out an empty graph with K equals 0, then the answer is yes. If the answer is no, empty graph, graph with one edge and K equals 0, then the answer is no. So we, after mapping to the new instance, so we have three conditions. Reduction should run in time, polynomial time, in the size of the input. So that means in polynomial time, the time polynomial in, right, computable in time only length of x. Okay, and in the books actually they write length of x plus k, but I will be lazy, just write time of for the time of x. Well, I mean, k can be a number in binary, and then, for example, for subset sum, yeah, actually, maybe I should not do this, but I will be consistent with the slide. So there are some cases. Okay, now I need to be careful with exercise, but let's just use the simple definition.
Okay. This is a completely function size.
Yeah. So the size of the new instance.
What is the size of the new instance?
Yeah. Okay. So the size of the X part of the new instance to be consistent with here. So it means let us say that's the size of xk, it's equal to the size of x. So here we look to the input part. Okay, I'm a bad person. I should stick with the definitions of the book. So my okay, but for now, let's fix it like this. It's just 3 lectures. We will not go too deep.
K X is an L, that's about K is an which means K doesn't screw up our problem, right?
Yeah, so we make the problem very small. It only depends on K is statically small, like 100 or something in the vertex covered problem. And even if X is 10 million, after the reduction, we end up with some function of 100.
So K acts on inputs, right? So we have a decider for our problem, let's say, and we have the inputs to it.
Yeah, the decider gets both K and X,
Yeah, so
the parameter and X. Okay, so this is definition of kernel. And now there is a nice theorem. So problem has a kernel if and only if it is in the class FPT. And the proof is very short. So so assume so so algorithm decides L. So that algorithm, that L could be an algorithm. That L side L in time as f of t times length of x to the power c. That L and c. F log and c, the triple from the definition of FPT. Okay. And now kernel K of x. Just run decider. So run this alg for time length of x to the power c plus 1. Output answer. So if this algorithm finishes in this time, then we can tell the answer. Just fixed instances for which is yes or no. And then otherwise, output kx. So that's the algorithm. So two rules. Run the decider. So this is the running time, but we run it for this time. If we get an answer, then we output the answer. Otherwise, we output the input itself. That's our kernel. So now we have to check the three conditions of definition of kernel. Oh, by the way, I forgot to tell there is easy direction in the theorem. So what's the easy direction?
Has a kernel dimension.
Yeah, and why is it?
Because
applying the kernel and then
deciding.
Yeah, so what is the runtime? F of the parameter, which is bounded by,
so
yeah.
F and S.
Yeah, the parameter should also be bounded by S. I forgot to tell you in the science definition. And then we have X, which is also bounded by K to the power C. And so this is a function that depends only on K.
The parameter should be bound by what?
Okay, so when I said that smaller Kx is smaller than, so what is this? It should be equal to the max of K and length of X. Sorry for this. Yeah.
So
Okay, now we see that, okay, I cannot, yeah. Okay, this is very messy. Okay, I will write notes to fix this and send it to you. Yeah, only about kernels I will write notes. Yeah, and I will update the slides if I can find the latte. Oh. Okay, but so now okay, that's the real definition. K plus length of x. It's the real definition. Now I'm not trying to be lazy and then getting into trouble. So it's the real definition of length of an instance. So we require that this is bounded by S of k.
Since they are both positive,
Yeah.
every each
Yeah.
one is bounded by s of k, and so the problem is in.
Yeah. Okay, and so what is the runtime? So we have polynomial. So I claim that if it has kernel, it's an FPT. Why? We run the reduction,
And then
which
we-
requires polynomial time, so we don't need to worry about this time. And then we run the decider. And what is the time of the decider? It's f of the parameter times the length to the power c. But here the length of the reduced instance. Okay, the length of the reduced instance is at most S of k. Yeah,
And the length of the parameter.
and the parameter is now also at most S of k. And so here we have something only depending on k, here also something depending only on k. So we get something better for the bound on the runtime. So when we combine both procedures, the decider of L has kernel. Oh. I see. Range and L is inside the ball. Okay, now it works. Then L is an FPT.
Where we get that f of the parameter and the power?
Yeah. I messed up. Okay, so decidable. So let H be the time for which is decidable.
Mhm.
So now we will apply. So H get a length and tells the time. So H is a function that, given the size of the instance, tells the maximal time to decide it. Yeah, I will write it more nicely. But then I need some space. Okay, so L is decidable in time. So H. So the question Kx in L. So this question is decidable in time H of size Kx. And H is some computable function. Okay, I understand now why we need computable functions. Okay, so and now we want to prove it's FPT. And we also know that L has kernel. So what we do, we apply the kernel, and the output of kernel goes to the decider that runs in time H. But after applying the kernel, the length of Kx only depends on the parameter K because of second condition.
Mhm.
So we can assume H is monotone. So decidable on all inputs of. So you understand, we can assume H is monotone, right? Because unfortunately we have inequality here. That's why we want H to be monotone. Polynomial time reduction to something smaller than this. And now this decision procedure, this computable function, the runtime only depends on parameter value. Okay, so what is the runtime of the combined procedure? It is kx to the power of 1 for the reduction. First, we need to make it small,
Okay.
and then h of s of k. And here I use that h as monotone because in 2 we have inequality. So this is the runtime. And this is really cool. So we have we went from polynomial, from function of k, from function of k times polynomial in x, we went to function of k plus polynomial in x. That's a really cool thing about kernels. Like the painful function gets separated as an additive constant. Yeah. So this is this direction. Unless I said it's not at all easy, and my statement was even wrong, and I messed up. So okay, for punishment, I will write it in the next days. By Friday, I will write it. Okay.
So now we do the shorting, the hard button.
Yeah, but now I think that this was actually the hard part. The other part, algorithm is easy. So if there are no questions anymore, I will delete this in the bottom. Okay, so now we assume L is FPT and we construct the kernel. And I already explained what's the algorithm. So we run the algorithm that decides it in FPT formula time. If we get an answer, we output it. If we don't get an answer, we output the instance itself. Now we have to check 1, 2, 3. So first, does it run in polynomial time? Yeah, that's clear because of this condition. Yeah. Okay, 1 is good. 2 is the length. Let us start with 3. Is it equivalent?
Yes.
Yeah, clear in both cases. Here we are very safe, and here we are safe also. So now 2 remains. So the question is the size bounded by a function only of k? So here we are good for 2. So here we just output the answer, so the size is constant. We just pick the smallest where it's yes, the smallest where it's. So here the size is a constant. Now here, this case, we have to check. It's the last task. Okay, so here we know that the runtime was larger than this thing. So what do we know? Here is our runtime. So we know f of k times length of x to the power c was larger than x to the power c plus 1. Look, we are done. We've proven x is small.
We have proven that f of k is larger than.
Yeah, so we cancel x to the power c here, and what remains, f of k is larger than size of x.
So. What? When did we prove that the first statement that f of k multiplied by?
That was in the other direction. So now we have something cool. When our problem is in FPT, we have a kernel, and then we went from times to plus. But that's kind of logical with these huge functions. If you multiply them, it's just like increase the power a little bit in one, in the largest side, and then yeah, it's not so surprising actually. So this is completely empty proof, but it tells us something interesting, that this cleanup will always be successful, even for stupid reasons.
Why do we care that f of k is greater than size of x?
Because we need the second condition.
Yeah.
In this second condition on the second range, we output
and X, and we need to check that the size of K and X is actually bounded by computable function of K. We know that the size of K and X is K plus size of X. The size of X is lower than f of K, which is a computable function. And obviously K plus size of X is lower than f of K plus K, which is a computable function as well, so we can just set.
So yeah, that function is the S function, kind of.
No, S function is f of K plus K. Right?
Yeah, because we need to.
Yeah.
Okay. Understand.
So we are finished for today. So this I will explain. It's not so much. I will start next lecture. And then we will have better kernel with size 2K next lecture. But that's not needed to program for now. Because it's with linear programming and it crashes on. So I don't know. So linear programming is unstable around 200 parameters and then the same number of inequalities. So when you program, you don't need to. So only things for today. Okay, the programming task. I do need to explain a little thing, but let's have a break now, and then I will explain a little bit.
How long?
Till 5 minutes, 15 minutes.
15 minutes.
Okay, so then I will explain a little thing so you can start with the programming exercise and we will do the exercise. So on the wiki there are sheets. But I forgot to print them, but for here I will write it on the board.
We can send this as many times as we want.
Yeah. It's yeah, but with my skills. I mean the grader, I hope it's stable.
There's a gentleman agreement not to DDoS the grader.
Packet.
Yeah.